Okay, next we have electrostatic boundary condition. As we know that the electric field at point P, suppose the electric field at point P, which is at a distance r from the point charge, is given by 1 over 4 pi epsilon naught q over r square. From this equation we can say that this electric field is inversely proportional to the square of the distance from the point charge. Now if I plot it graphically, what it means, suppose the point charge is here, this is the point charge and this is the distance r. As we move away from the point charge, then the electric field close to this point charge is maximum. This is the electric field direction. It's maximum. As we move away from this electric field will decreases in this way. Here close to this point charge, the electric field is stronger. As we move away from this point charge, then the electric field decreases, and finally at infinite distance the electric field will become 0. What it means? It means that suppose we have a point charge Q here, close to the electric field, close to the point charge, the electric field is stronger. So this arrow with length, greater length, means that the electric field is stronger here. As we move away, it becomes smaller and smaller, and finally it finishes. So this is the concept of electric field. Now if we introduce a charge surface in the direction of electric field, if let's suppose I introduce a charge surface, suppose this is the electric field, here I put a surface with charge on that surface, then what will happen? The situation will be like this. The electric field at the point charge is stronger, it reduces, decreases like this, but once we reach this charge surface here, then there will be a discontinuity in the electric field. The electric field will look like this. So across this charged surface the electric field becomes discontinuous, and this is called boundary condition for electric field. Boundary condition are electrostatic boundary conditions. Like if you introduce a charge on the path of this electric field, then this electric field become discontinuous. Here it decreases and then suddenly it increases and then again it decreases. So this discontinuity from this point to this point is called electrostatic boundary condition. Now here we will prove it, that once we introduce a surface charge in the direction of electric field, then this electric field will become discontinuous. We will prove it mathematically, and we will also prove that the electric field is discontinuous across a charged surface, but the electric potential is continuous. Electric potential will continues across a charged surface. So these are the two main purposes of this topic. Now I start from the electric field of a point charge without a surface charge. Suppose we have this point charge, okay, it is electric field in any direction, in all three directions, Now suppose I consider 2 points somewhere in this space. One point is this one and the other point is this one. these 2 points are very, very close to each other. They are almost overlapping each other. Here I shows the difference that they are apart from each other, but we suppose that these two charges are much closer to each other. Now I suppose that the electric field at this point is this one, and the electric field at this point is this one. I consider this is to be point 1 and this is to be point 2. Then this electric field is E1 and this electric field is E2. This is not a charge, this is any 2 points in this electric field in this region. I consider these 2 points here. So here the electric field is this one, here the electric field is this one. So I consider these 2 point charges. The point charges. The point charge is somewhere here, and I consider 2 points in this space. Now if I resolve this electric field, then this is the parallel component of this electric field, E2 parallel, and this is the perpendicular component, E2 perpendicular normal component. Similarly here this one is also E1 parallel, and this is E1 normal or E1 perpendicular component. Now since point 1 and point 2 are very close to each other, point 1 and 2 are much closer to each other. So we can say that electric field at point 1 is equal to electric field at point 2. There is a small difference, but we neglect that difference, and we assume that this electric field at point 1 or electric field at point 2, they are the same. Now if E1 is equal to E2, then what it means? It means that the parallel component of electric field at point 1 will be equal to the parallel component of electric field at point 2. And similarly, the normal component at point 1 will be equal to the normal component of electric field at point 2. This is the case with free space, like we are not introducing any surface in these 2 points. Now we are introducing a surface. Suppose we have these 2 points. In between these 2 points, I introduce a surface with charge, and on that surface we have a charge. So I introduce a surface here. So this is the surface, and we consider 2 points. One point is above this surface and the other point is below this surface. So this is point 1 and this is point 2, such that point 1 is above the surface because I introduced the surface here. So this point 1 is above the surface and this point 2 is below the surface. Now the surface has a charge density. This surface has a charge density sigma. Now what will be the effect of this surface on the parallel as well as on the normal component of electric field? So what will be the effect of surface charge on parallel and normal component of electric field? When there was no electric field, when there was no surface between these 2 points, then the electric field is continuous. E1 is equal to E2 because at point 1 the electric field is equal to at point 2. The normal component of electric field at point 1 and 2 are the same, and similarly the parallel component of electric field at these 2 points are also same. So there is no discontinuity. Now we will introduce a surface such that one point is lying above the surface and the second point is lying below the surface. And between these 2 points we introduce this surface, and this surface is a surface charge sigma. So here we will see the effect of this surface on this parallel and normal component of electric field. Now this surface, this is a surface and this surface is a charge. Let's suppose this surface is a charge Q. Then this surface has its own electric field. The upper surface electric field is upward. This upper surface electric field is upward, and this downward surface, like this is a surface, okay? This is a surface. This is the upper surface. This is the lower surface. This is the upper surface. This is the lower surface. If there is a charge, then the electric field here is upward, and here it is downward. So this surface has upper surface. This surface is two areas. One is the surface with top, and one is the surface with bottom. So the top surface is electric field upward, and the bottom surface is electric field downward. Now at point 1 we have two components of electric field. Point 1, one is parallel component and the other one is perpendicular component. Now the parallel component is this one. This is E1 parallel and this is E2 parallel, while the perpendicular components are this one, E1 perpendicular and E2 perpendicular. So it means that the components of electric field of this surface, which are this one, they does not affect the parallel components E1 and E2, this parallel, but they affect the perpendicular components, because electric field is a vector quantity and the net electric field will be E will be the sum of E1 perpendicular plus E is this one, E up. This is E1. This is E, yes. And this component direction is this one, and here the direction is this one. So E will be, I call it E1. E2 will be E2 parallel, E2 normal, which is this one. Its direction is this one. Here the direction is downward, so it will be minus E. So it means that this electric field of this surface affect the normal components, E1 normal and E2 normal, while it does not affect the parallel component, E1 parallel or E2 parallel. Now, for that we draw a Gaussian surface. Next we draw a Gaussian surface. Suppose we have this surface. The same surface as I plot here. The same surface as I plot here. Here we draw a Gaussian surface. This is like a pillbox. This part of the surface, this Gaussian surface, this spot is above this surface, and this part is below this surface. It's below this surface. So this is the direction of the surface. So this part is below and this part is above. And I suppose that this is area A, and it is a charge density sigma, and we suppose that this is the distance d, the width d. So one point is on the above part of this pillbox and the other point is in the below part of this pillbox. This is point 1 and this is point 2, like point 1 and 2 or like point 1 and 2, this one. So one point lies on this inside this box, and the other point lies inside this box, this one. And we assume that this d is much smaller, like the width of this box is much smaller. Now once the width is much smaller, according to Gauss law, the total flux E dot dA will be equal to the total charge enclosed by the surface divided by epsilon naught. We can say that E dot dA will be equal to, total charge will be equal to sigma times A. So it is equal to sigma times A divided by epsilon naught. Let's say this is equation number 1. Now here we have 6 surfaces. I will plot it again here to make it more clear. So this is like a pillbox. So it is 6 surfaces. One is up, the other one is down. One is this one, the other one is this one. One is this one, the other one is backward. So there are 6 surfaces. But we assume that this d, this width of this box is much smaller. It's much smaller. So it means that now if this d is bigger, then the contribution to the flux will be from 6 surfaces. One is up, the other one is down, one is this one, the other one is this one is this one, and the other one is that one. 6 surfaces. But if d is much smaller, like the width is much smaller, then the 4 surfaces will not contribute anything to the flux, because this area is very small, this area very small, this area is very small, this big area is very small. So we have only this surface left which contribute to the flux, and one is the bottom surface just below this one which contribute to the flux. So the total contribution to the flux will be E dot dA from the top plus E dot dA from the bottom, which is equal to total charge enclosed divided by epsilon. Now here we have point 1, here we have point 2. Now point 1 electric field is this one, normal component of electric field is this one, E1. So here the electric field flux contribution is due to electric field E1 perpendicular. And in the bottom case, the contribution from the electric field will be from this one, E2 perpendicular, from this one, because this surface is below, this point is below this surface. So it means that the contribution, also if we look at here, the direction of area of this surface is upward, it's parallel to this E1. Here the direction of this surface is downward, this downward, while the electric field direction is upward. So they are anti-parallel to each other. So we can say that on the top surface, the contribution is from the electric field E1, normal component dot dA, plus on the bottom surface, the contribution is from E2. naught, which is equal to sigma A divided by epsilon naught. Now even normal or perpendicular component N, dA are parallel. Okay, in E2 normal or perpendicular component N, area dA are antiparallel. Here the theta is 0, here the theta is 180 degree. So it means that from this I got E1 parallel into A, minus, here I got minus because the angle is 90. So cos 180 is minus 1. So here we got E2 parallel, normal into A, which is equal to sigma divided by A into epsilon naught. Now we can say that E1 normal minus E2 normal is equal to sigma divided by epsilon naught. This is one equation. I will continue in the next video.